Hello and welcome to the Braincast, episode 5. I'm your host, Brainmuffin, and today we're going to explore the wonderful world of random maze generation. One algorithm in particular, and that is the DepthFirst Search algorithm. Now, why this one as opposed to the scores of others, and there's all kinds of different ones? Well, DepthFirst Search can also be used to solve the maze itself, not just do its generation. There's all kinds of maze generation algorithms that deal with grouping cells together of a matrix and different things, but this one is pretty straightforward, pretty simple. So what we're going to do is show what the algorithm is about with some pencil drawings. We'll just show, kind of walk through the algorithm as well, and then we're going to show how to do this on the Applesoft BASIC program in low-res graphics, so that we can use the blockiness of the graphics to show how an algorithm can be generated from a matrix. Now, interesting aspects of this algorithm are its use of a stack and the concept of data structures, both of which are not available in Applesoft BASIC. So how we're going to get around it is with arrays and different things of different arrays holding different information for each cell, and some other neat tricks for that help speed this along. And we'll see that in code, and we'll discuss it as we go along. As always, all code will be on the website, brianlape.com. And we'll put a link in the description for the actual code. And we'll do another show later on where we'll use the same algorithm to solve that maze. And we'll also do some sort of animation, if you will, with kind of the snake as the computer tries to solve it. Now, the algorithm is pretty straightforward. It basically says if you have, let's say, a grid or a matrix of cells, two-dimensional, you can start anywhere and you can just start visiting neighbors and you start removing lines. And that's what we're going to do with the drawings. Will show us removing lines. Now we're going to start simple with a 3x3 matrix, and then we'll show some code. We'll probably show it in steps and stages. I know we could go for 2 hours, and you don't need to see me or hear me typing code out. It's really going to be a code discussion. And then we'll do it, like I said, we'll another show. We'll actually take that same algorithm and we will do solving. Now, obviously, I still do not have, I got Apple hardware, but it's Macintosh. I don't have actual Apple II hardware. So what we will be using is the emulator 2 on the Mac. We'll do some screen capture and things like that. Now, if anybody has Apple II hardware and would like to type this code in or get a file, we'll probably have it available as a data file too, or text file. The emulator allows me to copy and paste from text editors from the Mac into itself, so it's really easy to correct code and then paste it back in. Now, obviously, you don't have that on an Apple II. Now, if someone makes it available like through ADT Pro or something like that, please let me know, and we'll put it in descriptions and links in the description, and we'll also put it on the website, because I'll probably do a follow compendium article or a series of articles on the algorithm itself. So without any further ado, let's get to the sketching of how the algorithm works, the kind of a visual representation of the data items we're going to need to store, and then let's start looking at some code and get this thing solved. All right? Thank you very much, and we'll see you on the other side of everything. Bye. Now, the DepthFirst Search maze generation algorithm is fairly straightforward. For any given cell in a maze, let's say this is our cell, we have a potential of visiting neighbors if they haven't been visited before. And neighbors are identified as being either horizontal or vertical only, no diagonals. We're not doing diagonal mazes, so we'll list this. Any cell's neighbors may be chosen if it hasn't already been visited. If not, we mark it as visited, and then we get rid of walls. So let's take out an entire example of this and see what we've got. So let's just build a 3x3 maze using the ideas behind the DepthFirst Search algorithm, just to keep it simple. So the algorithm states we may choose any cell to start, but just for simplicity, let's just start here. And we'll make a check mark anytime a cell has been visited, and we'll erase the lines. So we visit it and we make a check mark. Now there are two neighbors, one here and one here, one to the right, one to the bottom. And we may visit either, but let's say that the algorithm decides to go here because they're both eligible. So we make a check and we remove the wall between them, which in this case is just our line for our drawing. Now this one has two as well, and let's say that the algorithm chooses here. We randomly just select. We go to the right. Now this middle cell has 4 neighbors potentially, but only 3 haven't been visited. So we can't go here, but we can go here, here, or here. Well, let's suppose that it goes down. We make a check, remove a line, we clear the crud, and all we're doing is smearing. But anyway, now this one has 2 as well. Well, suppose, because you say, well, what happens when we run out of neighbors? Well, let's suppose that it's chosen to go here. Now we have a cell that has 2 neighbors, one to the right and one above, but both have already been visited, so we can't select it again. So as part of the algorithm, it's a stack of cells. Each cell we visit, we put stacks, so we pop off, we go to the next one. Well, this one does have a neighbor to the right, and that's the only one that's eligible. So we must visit. Now here we are in this cell. We may go up or to the right, but that left rather, that's already been visited, so we must go up. Now we're here, we can go here or here potentially, but we only really have one. So we just continue on, and now, whoops, I'm a little ahead of myself. Each cell only has one potential selection at this point. And now all of them have been checked, and we go back through the maze, and lo and behold, we're finished. And so we have a solid wall here and solid walls here and here, and there's our maze. And it can also be used to solve the maze by only visiting things that have openings. So we have a concept. So what does that mean as far as storage? Well, we have one concept is we have a cell. And it has 4 walls, potentially has up to 4 neighbors, so we have to keep track of where the neighbors are. We also have to know if it's been visited. And we have to know which walls are still up. And as far as when we do the algorithm, we have to have a stack of cells so we know where we've been. And we also need to know when we're back to the first cell. So basically, when we have an empty stack, we're complete. So if this cell has all of its neighbors have been visited by one form of another, and we pop it off the stack, and then we look at this cell, and then its neighbors by any path has been visited, and we pop it off, and we're back to here, and all of its neighbors have been visited, and we pop it off. When we have an empty stack, we know all neighbors, all cells have been visited. There are no more neighbors to go visit, and we are done with our algorithm and our maze generation. And the data remaining is the shape of the maze. So what's that look like in computer code?
Now it's time to look at some code, and before we worry about graphics and things like that, let's just try and understand how we want to save some mechanisms and some data of which parts of the maze, what cells have had their walls removed, and the like. Now in Applesoft BASIC, we don't have the concept of a data record, but we do have arrays, we have strings, we have integers, things like that. We also don't have the concept of doing any bit twiddling. However, if you look at the values 1, 2, 4, and 8, which are all positive powers of 2, they add up to 15, which is very convenient. And if you subtract the value, this is part of what we're doing here on line 25, If you subtract one of those values and you subtract them in the right order, you can tell what parts are there and what parts are not. So if you get a negative number, you know that that part has already been removed. So the concept here is we want to store our values. Here we do some setup. This is really just kind of a text run of setting up the cells of a maze. Now in this example, if you look at line 10, we're saying the row size is 3 and the column size is 4. So we basically have a 3 by 4, so we end up with 12 cells. Applesoft BASIC lets you start counting at 0 and 1. So this is actually written to basically get everything at 0. So there's a minus. And the other side of this is how we're going to store the information. And so it would help if I did a listing of the right way around. Yeah, that'll work. A little slower, but it'll work. So the print routine we'll really kind of skip over, but line 200 is where we're defining where we are, what our current index is. We're going to use an array to have a stack, and now we're going to have to simulate a stack using an array. But by the way we change the index will be like we're on a stack, and then we have a visited stack, which basically is the size of the stack of the CI. So CI is how many pieces we've got and the like. So that's going to grow dynamically. And we're assigning that very first value to 1 because that's where we're going to start. Now this thing is not going to actually create a maze. This is really just the setup. So if I skip back to the top here, this is going to step through. So we're going to use a couple of concepts. One is that on a square, if we go up, we're going to call that wall, we're going to give it a value of 1 in every cell. So we're going to use the power of 2 to understand this. If we go down a wall, we're going to use that as a 2. If we go to the right, that wall is 4, and the left wall is 8. That's what you see in line 25. Line 20 are the neighbors around. And basically what we can do is we can calculate whether, because certain cells do not have neighbors in various positions. Along the border, the central cells are only going to have 3 neighbors, and the corners are only going to have 2 neighbors. So that's what, and what we're going to do to assign that is give it a value of -1. And that's what you see on line 50 where we're initializing the maze. We're running through everything. We give it all as a -1 to start, and then we go through basically starting with row 60 where we go from the rows and determine what the neighbors are. So we can calculate the neighbors basically by multiplying the number of rows and the number of cells. This is where starting with 0 is helpful, and then adding the number of columns, which we calculated, I think, the column number that we're currently at, and that will tell us various neighbors. So this is and I'm trying to remember what RN was, but when we run this and we spit out the result, this is kind of what we're seeing. So cell 0 there, it has no neighbor to the left, or no neighbor up rather. That's the up one. It has a neighbor down, which is cell 4. It has neighbor cell 1 to the right and has no neighbor to the left. And the 15, it means that all of its walls are still there. And so that's calculated through those loops and those if statements to figure out, which one of these do we have a value to put something in and which we don't. Now with Applesoft BASIC 2, when it comes to the if structure, it also doesn't have a concept of if then. So the if then else. It has if then, but not if then else. And it's anything from that line on in that line. So if we have a compound line, so we can't really collapse these too far. So if our column is going to be less than the size -1, then I forget what RN is. That's row number. That's the column. And you also only have 2 significant characters on variable names. So it starts to, with this particular thing, it starts to run into each other. So that's just a very quick kind of concept, but we can utilize this concept with the text. Now, obviously, every time you run this, it's going to be the same because all it's doing is setting up. It's not trying to create a maze. But we can actually use the concepts and the text output here to determine our algorithm and code it without actually creating any graphics. And that's what we'll do next. Okay, now this code, we just basically, this is going to add to what we just looked at, and we'll put all the listings out on the websites and links and all that stuff. So this is really just a code overview. We're not going to go into extreme detail, but the concept here is we're going to add in ways to remove walls by DepthFirst Search, and then we're going to see text. We'll see it actually come along. So we're just going to quick overview because this is a lot of code in here, but it's still that same concept of a stack that we saw in the other listing and a visited stack. And our CI is essentially our column, or basically it's our stack pointer, if you will. And that way we can try and keep these things all set together because there's only going to be one index that sets the current index for both sides. Again, we have to do this because we can't use a data structure, otherwise it'd be a little bit easier. So the basic concept is this is going to start in upper left-hand corner, and it's just going to work its way through. Now we're still dealing with the same size of our the 3x4 matrix for our layout, and now this is shown in 80 columns on this emulator, so we can show it in 40 as well. It's a little easier to look at the text that way. So basically on line 260 we're choosing a place to go that's random. Basically that's the neighbor index. Now remember, there's, because of our data structure where we're basically saying a cell is it's a two-dimensional array. Actually it's more than that. It's a five-dimensional, I don't remember now, but I think it's two-dimensional array, and we have our current one, and we're going to look and see because 0 through 3 is where all the neighbors are, and we're going to see if we've visited that neighbor already. If that neighbor has been visited, then we'll just go on with life. So that's what is happening in the 265. We're saying, hey, have we been to our neighbor already, based on that random number we generated on 260, and if it basically if it doesn't equal 0, then we're going to set it to 1, and we're going to go to line 690. And that's a go sub, and I think, if I remember correctly, 690 is just going to go, it's just going to really print out. We kind of push, this is part of why we pushed that go sub routine pretty far out in the other listing, is so that we could kind of fill in the details here. And that's not a long enough collection. I kind of got a little carried away with my numbering. But that's basically what we're doing in any direction. Is this? Did we choose a neighbor that's either left, right, up, or down? Have we been there? If we haven't, and it's also determining whether or not to mark cells. So these are this is why we're doing this with this array. We then in line 400 set things to visited. We then essentially for our cells. Basically, because remember our cells is a two-dimensional array, our current stack is going to hold the index of that cell relative to the cell listing. And remember, since it's a two-dimensional array, we're flattening the matrix, the 3x4, into 0 through 11. And so we're making a run on basically a one-dimensional array of the two-dimensional matrix, and then we're adding the concept of we have 4 neighbors, and each of those neighbors can have a value. And then we increase our essentially our stack pointer, and then this is what we're doing in 410. We set things to -1 because we've been there. 420 we increase our stack, and that's what we're basically, our stack counter, basically current index on the stack, and then we're pushing into the stack where we just were, because that's when we backtrace, it's where we need to then pick up. And that's the rest of that, and then we print it out, and then the CI, if it's greater than -1, we're not done, and then we go to line 220 and start all over again. So this is how we know how, if we've accomplished everything. This kind of starts things again. It then chooses another one, and it goes on. So if it doesn't find any neighbors, then it pops it off the stack, and then continues on as well. So let me stop talking a little bit and just kind of run this. Maybe this will make it a little clearer, and we'll pause it here. I'll break it. It's probably going to change all the numbers. But here we have a couple different runs. So we have cell 1. See, we're starting to see other numbers in here. So 0 and 1, and we have a 7. So a wall was removed. And based on the 1, 2, 4, and 8, the only way it gets 7 from 15 is if we subtracted 8. So we took away a left wall on cell 1, which makes sense because cell 0 is to its left. And if I had stopped a little sooner, you would see that. Now you do kind of see that here, because now it's actually chosen. So it went across, and then it's selected. Where am I? I'm losing myself. So it has no neighbor above it. The neighbor below is 4. The neighbor to the right, it was, instead of having it as a 0, we now mark it as a -1, because it essentially means we visited. So the concept is we're stating we visited outside the maze when that's not really true. And because it was a 4, because the neighbor to the right is, we're calling that wall number 4. It's a power of 2. So remember, 1, 2, 4, and 8. That's how come we have 11. And then on 1, it's now done another wall. We're down to 3. So it chose, before it chose an 8, and then it chose a 4. So it chose to go to the right, if I remember correctly, because it's that's the next neighbor we visited. It chose to go to the neighbor to the right, and then its neighbor to the right is not sure what it is. So it's up, down, left, right. I chose to go to the 4. Anyway, so let's just let this run. I'm kind of confusing myself. I mean, I obviously wrote this as a way to test my algorithm, and it gets kind of confusing. You can kind of visualize where things are going, because you can see the numbers changing as things become -1. Now, obviously, when it's done, we're not going to be fully, everything's not going to be a -1, because, well, all of the cells should have a visited of -1 in the visited stack, but in this piece, they won't all necessarily be -1. I don't think. Well, no, I guess they should all be -1 because they've all been visited, but they will have different values of walls, and you'll be able to tell. So that's actually what we're saying here. So I'm going to speed this up because this takes quite a while. And now there we go. So there's the last output. I was correct. I remember it gets all -1s, but based off of this, we can now draw, if you want. You could take this and draw the maze, and that's one way to do this. Now I wanted. All right. So this version is actually a couple of jumps from the previous one, and although some of the things are actually still here that we've seen before, I'm trying to get. So one of the ways to speed up your coding in Applesoft BASIC was to put a lot of declarations at the bottom. Basically, you want things that you're going to call very often as close to the top as possible. It creates a linked list of, in Applesoft BASIC, it creates a linked list of all the line numbers, and so anytime it has to traverse that, it takes a while. Now this is not fast, although we're going to speed it up once we can see what's going. So well, here's what's going on as well. So here we have our initialization of our various counters. In 12, 5, 10, we have the setting of the row size and column size to 19. So basically we're creating it's what's going to result in a 20 by 20 maze because of the drawing on the outside. So But we have 19 cells, but we only have 20. We only have 40 columns essentially, but we are going to draw around each cell, and the walls will overlap. So it's not like we need 3 times the size. We only need about a little bit more than it is on the actual, and a little more than double. So double that is 38, but then it gives us a border. Now it makes one column on the right-hand side not in use in low-res graphics, but that's okay. And the CI have we seen before, and we have some other dimensions of our neighbors left. That's the 4, 2, and we have the neighbor to the up and down and left and right, and the same thing we've seen before. We have the number of columns as the number of the row size times the column size, and we're dimensioning things this time, and the visited and the stack and everything else, and then we return. So if we look at the first bit of code, obviously it calls that, it sets up the routine. We're going to run it in green basically, and then we remove the walls by DepthFirst Search. So the wall removal routine looks very similar as we saw before, except now this time when we remove a wall, we're actually going to plot a point. That's why we set the color to 0 at 225. And I actually made a version of this where I chose a random number for every cell when it was drawing, which was a little bit different. This actually draws them by vertical amounts, and I forget exactly where that is at the end. We'll just list this whole thing. It is kind of long. There's some remarks. There's more efficiencies that can be put in here, that's for sure. And so we initialize the neighbors, and then we go on. Now, because this is a little bit larger than what we had previously, where we just had a 3x4, and we have a 19x19, this does take a little bit more time. The other thing this thing does is it also randomly selects one of the cells to start. We can start in the upper left like we did with the text, but eventually what I did is I made a version that does this, and will just randomly chooses. Now this is running in real speed on the emulator. I did put it in ProDOS so that I could compile it sometime, and maybe I'll do that. I'm not going to do it in this video, but it does start drawing, and it generates the maze. And again, here you can see it going from square to square. It's looking for which neighbor to choose, what hasn't been visited, which wall to remove, and then when it gets stuck. So this is all building in a stack. This is all, it's pushing all these values, and then soon I'm hoping, there we go, well, it cycled back on itself, which is fine. It can do that, but it hasn't. Here we go. So now it's going to have to back up, and then it found a way around, and now it's definitely going to have to back up. So now this pause that you see is it backing up, and there it found another way, and now it's gotten out of that space. But it will visit all the cells. So this cell right here that's visited, not visited, will obviously be pulled back at some point. These two will be visited. This one will be visited. I don't think the mouse pointer is part of the recording. But this does take a while. But this is because I wanted to visually see and watch the maze. So what you could do is take that maze generating piece, of what it's doing right now on the text side of things, and then just using those results to spit out the correct walls all at once. The one other thing that this algorithm has, another nice feature, I mean, it is slow. It does sometimes produce long runs, as we see, but it can be used to solve any maze. So given 2 endpoints, so now it's backing up again, it's popping stuff off the stack, now it's backing up again, and that takes time. And the other thing I'd like to do, and I'll probably do this, maybe do this in a future podcast, is to rewrite this in C. And I do have a C compiler. The graphics routines are what I got to find. So I don't know about making it machine language. That might, who knows, maybe. But definitely writing it in C would be a lot faster and to be compiled. So here's what happens when I click the button to go 3 times faster. It obviously finishes very quickly, and there we have it. So now every time I run this, it'll start. It will do. In fact, I will put it at 2 times speed so we can actually watch it run again while I'm wrapping up. But it's going to select a different starting point every time. Well, a random starting point, but it can definitely build a different maze. Theoretically, there's thousands of combinations that it could do. It's probably going to run into certain patterns and things over and over again. But it also means, and I have done this on a version on a different BASIC platform, is it can randomly choose a start and an end. So it could randomly remove a notch, if you will, from one of the walls anywhere and to anywhere. Usually you want to do left and right and up and down so you don't have them on the same wall, and it's a very rudimentary maze to solve. But the concepts are going to be the same. It's going to go, where have I visited and which walls am I allowed to traverse? And then go to that new spot. And it doesn't necessarily have to randomly select, but it's going to look and see if I haven't been there, and I can go across the wall, and then it's going to look and say, hey, is this where I want to be? No, it's not. And it just keeps going. And that's how that DepthFirst Search can also solve the maze. So let's crank it to 3 and just watch it build a couple really quickly. So this is running 3 times faster, you can see, and there we go. And just one more time, and we will go back to the studio and finish out this episode. See how quickly that is? But you see the long runs and things like that, and that's what some people don't like about this algorithm. But its simplicity is quite nice, and it can be used to solve the maze as well. Where many of the other generation algorithms, all they do is generate an algorithm, but then you can use this to solve that other maze. All right, thank you. All right, so I like contradicting myself when I actually looked at some other code. So this is actually the first version of this routine. I thought I had done this, and then this is what happens when I do things and I wait way too long to finish them. So what you're looking at is the change in code. This is it's still a graphics routine, but this is actually the very early one. Instead of having it draw while it was removing walls, this one does it afterward. So it does all of the same things that we saw in the text-based version as well as the other graphics version. And then it goes and figures out which walls to remove and which ones to leave alone. So this is why you have the wall. We have a wall width, and we have the x coordinates. Remember, I can say 2 times the columns plus 1 for the x and y. This is actually can make calculations of everything. And so the WW is the walls values that are still there. What walls? So these are the ones that default to 15 because all the walls are there, and then we remove values over time. And if we remove the left wall, the right wall, and if it's less than 0, so I knew I had this somewhere, then we know to plot a point with basically it says this color is 0 and 830. It's going to remove the line from contention. And then the very next line, we've got to remove that value from the WW. Now, not in our storage, but in our copy, essentially. And then we keep going. And so anytime it's less than 0, we know the wall was removed. If it's greater than 0, the wall wasn't. But we still have to remove that value so that the next calculation will be correct. And then, so as a result, now I'm going to speed this up because this is normal speed. Everything else this is all the same as we saw before, establishing the cells and determining neighbors and all that other stuff. But it's going to have a long pause before it does anything because it is generating the maze. And this is basically when I did this, I was like, oh, this is really a lot slower than I thought it was going to be. And I just sat here and waited. So we're going to crank this up to 3 times. And then as soon as hopefully it starts to draw, I'm going to slow it down so you can see what it's doing. Because at 3 times speed, it's so fast. See, I barely got it. But there it is. It's going row by row, determining which walls to get rid of. But the maze itself was created in a DepthFirst search. So, and if we run it again, we'll get different values. In fact, I can now that you've seen it in slow motion, we'll just run it at full speed. It does generate the maze a little faster because it doesn't have to do all the graphics stuff. But again, what this shows is once it's created, we could save these as a text file and then load the text file in at a later date and show the maze. So we don't actually have to create any graphics nonsense. So there you go. There's 3 times speed. It's pretty quick. It should be random. What I don't remember is if it randomly selects an entry point, but it doesn't fully matter really. So there you go. So and there we have a really long run on the bottom. But there's an example of, yeah, it's nice to see it as a graphics, but you could do it as a setup routine and then display the whole thing at once. Okay, hopefully this is the end of this discussion, and we'll go back to studio.
So that wraps up our discussion of the DepthFirst Search algorithm and how we can use it to generate a random maze, in this case on an Apple II. Now, I have gotten some feedback on some of the other Braincast shows of people wanting to know, can we do this on a Commodore? Can we do it on an Atari? And I have been looking for emulators for those. Now, even though my high school back in the day had Atari 800s, I did very little coding on the Atari. I had a couple diskettes. God knows what I ever did with them, because I don't. And so some of it's going to be from memory. I had a friend when I was in 9th grade had a VIC-20, and another friend had TI-994A. But once I left Maryland, everybody I knew had Apple IIs. So that's why the Apple II is kind of the computer I knew. I mean, I did some Apple II stuff in Maryland as well at school. And so we'll look at how we can, now some of this stuff is going to be a straight translation. Really, it's going to be how do we do the graphics. And I really look forward to some future shows where we take the Applesoft low-res graphics and we make this happen on an Atari, or we make it happen on a Commodore. Now there is a basic interpreter compiler-ish thing. I think it's called Basic 256 that I've used with Linux. And I've done some things with it. I got to find that code. We'll dig it up too, because it can do much larger mazes. But it's really interesting to watch it draw some things. Basically, I think we did it. I multiplied everything by 10, because what was a single pixel, which is fairly blocky on low-res graphics, is like a 10 by 10 on that screen. So that was pretty good. So we'll also in future episodes explore these concepts in a more object-oriented way. We'll have objects that represent the cells, and we'll actually have a stack object and pop all those things off, so we can show it in more modern computer programming. I just haven't decided what language I'm going to do it on, but that'll be for a future show. So thank you so much for stopping by and watching episode 5 of the Braincast. I've been promising we're finally getting back to these. Please let me know what ideas you want to see in the realm of computers that's a little bit different than what other people are doing. LGR and 8-Bit Guy, they have great shows about hardware and some of the software and games and things back in the day. But let's kind of take this in our own and maybe explore them, maybe even someday make our own game. We've got assembly language on the Apple II coming up. We've got graphics and assembly language on the Apple II coming up. And we'll start exploring other 8-bit computers from nearly 40 years ago. All right, thank you very much. Thanks for sharing. Thanks for all the feedback and the comments. And we will see you on the next Braincast. Goodbye. And we'll make a mark, and then we'll randomly choose a neighbor here or here. And let's just say we go this way, and then we erase. And then let's say that we have a neighbor. Let's say we choose this one. So we'll just go straight across, and we erase this wall. Makes it way too blue. Did this turn off? Nope. All right, let's go. Episode 5.